Hello. Today, well, like the title says, we're going to learn about finding the area of a regular polygon. Notice it doesn't say regular hexagon, pentagon, or any other particular polygon. That's because the formulas we're going to come up with work for any regular, say, n-gon. It could have 100 sides, could have 4, although we've only got 3 or 4. We've already got formulas for those. For 5 or more, that's a little tougher. It's not so obvious. Like rectangles are pretty easy. You just multiply the length times the width and you got it. Pentagons and on up, they're not so obvious. However, if we were to do something similar to what we've done before, we could break our regular polygon up into triangles. And, for instance, this triangle right here, this is the radius, so if we were to come bring a line from here to here, that would just be another radius. And the new triangle we would form would be congruent to this one. This is a hexagon. It has 6 sides, so there are 6 of these congruent triangles all the way around. It would completely cover this thing. For instance, this is one side of the triangle, and here's another side, so if we drew one line here, another line here, in other words, if we just went straight through and had a diameter of the circle, this triangle would be congruent to this, which would be congruent to this. If we went all the way through, we'd have 6 triangles, just like this one. Well, we could make use of that, seems to me, if we figured out what the area of this triangle was. We just multiply by the number of sides we have. In this case, it's 6. It could be 5 on up. Well, if we're given A, S, and R, we'll just start that way. We don't really need R right now. If we were given A and S, well, what's the formula for a triangle? This A is an altitude for this triangle. For a regular polygon, this is called the apothem. Why did they pick that word? Well, not sure. According to what I read, apothem became the word used in the late 19th century. It's from the Greek, meaning put aside or deposit. What that has to do with the altitude of the triangle you can form by connecting the vertices of a regular polygon, not obvious to me. So if you're wondering why it's called an apothem, you're going to have to ask somebody smarter than me. It just doesn't. The Greek word for put aside or deposit, it's not really obvious why that would be the word chosen for this segment right here. So, next time you meet a 19th century mathematician, ask him why in the world they chose that word for this. For now, it's called an apothem. I think we spelled that this way. Although this isn't a spelling class and you may not ever have to actually write that word down, just label it and call it A. What the heck. If we're given this, we already know that the triangle is going to be 1/2 A times the base, which is S. So we know the area of this triangle if we have A and S. Of course, most of the time, they're not going to make it easy for us and give us everything we need to know. They'll probably give us S and maybe the radius. Suppose we had that, then what would A be? I don't mean... Anyway, what would the apothem be? Well, we would have A is, well, we just use Pythagoras' theorem. If we knew S and R, well, remember this side is only half of S, so this would be S over 2 oops, This leg here from Pythagoras would of course be the square root of r squared minus s over 2 squared. We just want this half of the base this time. So we could do that to find the apothem. There are other times when you can figure out this angle pretty easy. Well, actually you can always figure out this angle pretty easy, similar to what we've done other times. There are 360 degrees all the way around. In this case, they're broken up into 6 congruent parts, or angles. So for this, it would be 360 over 6. That would be this angle here. This angle for the triangle, the vertex angle for where the center of the polygon or the circle circumscribed about the polygon. And that circle is just there to help you visualize what's going on. It's not a necessary part of anything, really. Well, if this angle here were 60 degrees, then this one would have to be 30. After all, this is perpendicular, bisects this angle. By definition, that's what we wanted it to do. That's how we get the distance from the line to the vertex. Well, and that's also because this is r and this is r, so it's an isosceles triangle. The perpendicular distance will also be a perpendicular bisector of the opposite side and a bisector of the angle. Suppose we just knew s. Well, let's see here. The sine of 30 degrees is opposite over hypotenuse. So if we wanted to find r, we could use that. But chances are we'd be looking for a. So if we know this is 30 degrees, opposite over adjacent, that's the tangent. Remember? Some old hippie. First letter s, that's sine. Opposite over hypotenuse, got another hippie. Cosine is adjacent over hypotenuse. And then tripping on acid. Tangent, opposite over adjacent. Here's the opposite, which is s over 2, and there's a. So we could also write that the tangent of 30 degrees equals s over 2. We only have half of the side now. Over a. Or, in the end, we could write a equals s over 2 times tangent of 30 degrees. We just divide through by the tangent, multiply through by a, and that, the little arithmetic, and it all turns out to be s over 2 times the tangent of 30 degrees. That's because s is the entire base here. If we actually use some other number for the half distance, instead of s over 2, we just use something like x, then it would just be x over a tangent of 30 degrees. The 1/2 is in there because we've cut this in half. But suppose we have the apothem. What do we do now? Well, like I said, it's pretty easy now because the triangle is 1/2 AS. How many of these do we have? Well, for a general polygon, we're going to have n of these. For instance, the hexagon, it's 6. And there's your nice simple formula for the area of a polygon. A is the apothem. S is the length of the side. You see what we're doing here is this part right here, this is just the area of one of the triangles. And this is just how many triangles we have. You'll see this rewritten sometimes as 1/2. Well, that's not 1/2. 1/2 A times P, where P is the perimeter. But the perimeter is really just the sum of all the sides. For instance, if we had a side length of 10 here, the perimeter would be 6 times 10 or 60. Real easy. Well, we got n here and the side length here. So n times s is the perimeter, the number of sides times the length of the side. Remember, we're talking about regular polygons here. If this was an irregular polygon, this wouldn't be true. You couldn't say that Sn equaled the perimeter. In fact, you would have different s's for different sides. In other words, the sides wouldn't all be the same length. In that case, you'd have to use our old summation symbol. Remember that? We'd have to write, I don't think you'll see this, but you could write the sum of s sub I from 1 to n, because each different side, you got side 1, side 2, side 3, on up, say, side 6 for a hexagon. If it's not regular, each of these little s sub i's are a different number, and you just have to add them up. However, if they're all equal, if you just drop the I here, the sum of s from 1 to n, well, that's automatically n times s, because it just means you're taking s plus s plus s plus s n times. So with these two formulas, as sloppily written as they are, we can find the area of any regular polygon. Yeah, talk cheap. Let's work some problems and prove that. Okay, here's a mistake somebody made. They don't know who, because, well, actually we just found this problem written on a bathroom wall. It was done anonymously, and they made a mistake. What was the mistake? Yeah, let's take a look here. 15 squared minus 13 squared. The square root of that should give us this section right here. There we go. Makes sense. 15 squared minus 13 squared. Take the square root and you get this. So this is 7.5. What does our formula call for? 1/2 of the apothem. Well, that's right here. That's 13. Times n. Well, we can see it's a hexagon. So n is 6. Seems like he's doing fine. Times s, which is, well, wait a minute. He found this section here. That's half of the side. You need to take 7.5 and multiply it by 2 if you want s. So we should have taken 1/2 of 13 times 6 times 15. So to get the right answer, it should have been 1/2 times 13 times 6 times 15. So if you wanted to know what the actual answer was, you could do all this, or if you're willing to believe that aside from this one small mistake, you did everything else right, in other words, the arithmetic here is all correct, well, 15 is just 2 times 7.5. So if you took the erroneous answer and multiplied it by 2, you would get the correct answer. So you could redo all this, or just take what he already did and multiply by 2. If you're pressed for time on a test, it would help you to spot this. Just multiply this one by 2 and boom, you're done. Well, I think that to work this problem, the first thing you need to do is look up dodecagon. It's not a word I hear thrown around a whole lot. Well, it's probably because you don't see a whole lot of them. I mean, if they were more common, you might hear the word more often. A dodecagon, that's a polygon with 12 sides. So the first thing, we could draw the triangle that we're going to use. We don't need the whole dodecagon, but let's just say that this is one section of that dodecagon. This is one side with side 8. And this is the apothem, and wow, you get the idea. And these two are both equal. These are both r. Yes, if you were to try to make sense out of that and believe that the way it's written, I think it might drive you nuts. I just don't draw very well. Pretend that these are both the same. This is right down the middle. So this is 4 and this is 4. You got to use your imagination when you look at the things that I draw. That's good for you, I hope. Now that we know, we're only given one measurement here, but I bet we can figure out these angles here. First we'll figure out the big one, and then we can cut it in half, and we'll know what each of these angles are. Well, what would the big angle be? We've got 12 of those triangles, so it seems to me if we divide 360 by 12, we'll get 30. I hope that's right. Yeah. Well, if this big angle is 30 degrees, this one here must be 15. Why do we care? Well, this is 4, and this is 4. We could use either side. Well, if this angle is 30 degrees, 4 over the apothem, we'll call this A, would be the tangent of 30 degrees. So we've got the angle, so we can look up the tangent of 30 degrees. And we've got this opposite side here. Tangent is opposite over adjacent. We just don't have A. So that's pretty good. We've got an equation we can set up with just one variable. It involves a tangent, but that's okay. Our calculator has tangents on it, or you can look it up. But not 30 degrees. We want half of that, because this is the right triangle, not the whole thing. So the tangent of 15 degrees equals opposite 4 over A. Or we can multiply through by A, divide through by the tangent of 15. A equals 4 over tangent of 15 degrees. And notice, just like on your standardized state exam, if you got in a hurry and didn't pay attention, you might write that tangent of 15 degrees equals 8 over A, because we got one side here equal to 8, and forget that you only need half of that. And what did they do? Well, they put that answer in there, so if you got confused, you might grab this answer. It's one of those good-looking but wrong answers. If you glance down here, you go, oh yeah, okay, opposite or no. Same thing over here. If you made a mistake and forgot to cut this in half and use the whole angle, you would get this one. So here's two right here that are very common mistakes, A and C, and they put them in. So all I'm saying is, when you take the state exam, be very careful about stuff like this. They're going to throw in answers that at first glance look pretty good. They're pretty smart. It's too bad. I think it would be a lot more fun if the people who wrote the state exams were kind of dim. That way they'd be easy to beat and you'd get really good grades. Instead they have really smart people make up the questions, and they throw in tricky stuff like this that makes it easy for you to get something wrong. Well, here's one that's not bad. Although I think the first thing you probably have to do is look up nonagon. A nonagon is not something that isn't an agon. It's not like we have agons and nonagons. If it's not an agon, it's a nonagon. No. Nonagon means a 9-sided polygon. And all they gave us was the perimeter, which is 18 inches. Well, I'm not sure the fact that it's a nonagon is all that important. Can we figure out the area of a regular polygon if we know how many sides it has, and the perimeter? I think the answer to that more general question will be answered if we try it with just one particular one. In this case, a nonagon. So let's draw a triangle. This is not to scale or anything, it's just so we can see what's going on. And this triangle represents the one created by joining the center of the pentagon, or pardon me, the center of the nonagon, or any other polygon, to two adjacent vertices. What's this angle in here? Well, it depends on how many sides we have. In this case we have 9 sides, so that big angle is going to be 360 divided by 9, which is 40. And we know that this is 2 inches. If we drop this bisector down here, and we know it's a bisector because this triangle we draw here is always isosceles. This is what's called the radius of the polygon. So our perpendicular distance from the opposite side to this vertex is going to be our altitude, which we call an apothem in the case of a polygon. It's also going to bisect the angle. We know that because it's an isosceles triangle, and the angle bisector will also bisect the opposite side. That means this is 1, and this is 1, and this here is R. Well, if this whole thing is 40 degrees, we've bisected it. And we've got 20 degrees here. So, what can we do? Well, it seems to me we could find A by using the fact that the tangent is the opposite over adjacent. We have the opposite, and we have the angle here. So it looks like we've got most of what we need to find A. In fact, I think we have all of what we need to find A. It's tangent of 20 degrees equals opposite over adjacent, 1 over A, or well, we've got tangent of 20 degrees is 3.64. If that's inverted, 1 over 0.364 is 2.747. So this is A. Now we have that formula that goes 1/2 A times NS, the number of sides, times the side length. But this is just the perimeter, isn't it? So the 1/2, gee whiz, 1/2 A times P, because they gave us P, so what the heck, let's cut down one calculation, even though 2 times 9 ain't much of a calculation. Let's write it, 1/2 times 2.747 times 18. Oops. And we can cancel this and write this as 9 times 2.747. And my calculator says that's 24.7. Did they give us, 8 inches, okay, so it's inches squared. So it looks like the answer is yes, we can find the area, and it's 24.7. And that's pretty much, in fact, I shouldn't say pretty much, that is true, period, for all regular polygons. If you got the perimeter, you can figure out. Some are easier than others. For instance, if they gave you the perimeter of a square was 24. Well, you divide that by 4, get 6. 6 squared is 36. Boom, you've got the area of the square. Nothing to it. For more-sided polygons, 5 sides, 6 sides, and on up, it's a little more complicated, of course. But we could always take the perimeter and divide that by n. And that'll give us S. Once we've got S, we can lay this out. This will be S over 2. We'll have S over 2 over A is the tangent of, and this will be 360 over n, divided by 2. That's what this will be. So we could lay this out in very general terms, pretty easy. And it turns out, for any regular polygon, if you've got the perimeter, you've got everything you need to compute the area. But don't forget regular polygons. Use this as a great big capital R. If these are not regular, if you're not talking about a regular polygon, nothing I just said would be true. It has to be regular. That's an extremely important part of everything that we're saying here. If it's not regular, you got a problem. As long as it's regular, you can do all kinds of stuff. Figure out lots of things with nothing but the perimeter or a side length. Maybe even a radius. But don't forget, it all hinges on the fact that it's regular. We say it so often, we just start to forget we're throwing the word regular in front of all our polygons. Don't forget that. It's extremely important. If you don't see the word regular in front, most of what we're saying won't be true. Well, they call it coordinate, but do we really need the coordinates to solve this problem? For this, you know by now you can automatically spot. This is a circle with radius 5. That would be square root of this. Centered at the point 4 minus 2. Now for the area of a regular pentagon inscribed in this circle, ask yourself, is area position dependent? In other words, if the circle were centered somewhere else, would the area of the circle or the pentagon inscribed in that circle, would they be any different? Well, no. The area is not position independent. I think I've pointed that out before. If you survey your land and take the origin to be the southwest corner of your property and go from there, you will get an acreage, say, for your land, the total area. Well, the city might start their coordinate system and put the origin at City Hall. So the coordinates for your land would be completely different from the coordinates you used, but the areas would come out exactly the same. It seems kind of reasonable, because if that weren't true, then surveying would be kind of a mess, wouldn't it? If people were constantly getting different answers just because of where they decided to put the origin. But it turns out how you lay out your grid doesn't matter. You'll always get the same area. Well, where you put your circle or your, in this case, what is it, a pentagon, doesn't matter where you put it. You're always going to get the same area. So what are the salient points here? Well, the radius is 5. It's inscribed. Remember, the vertices of our pentagon have to lie on a circle with radius 5. So here's 2 points on that circle. And here's 2 crooked lines that are going to pass for radii. Here's the chord that connects the 2 vertices, which are, I call it a chord because there's actually a circle here, and this is going from one part of the circumference of the circle to another. They're given R. They gave us R. That's 5. Okay. That's because the radius for the inscribed polygon is always going to be the same as the radius of the circle in which it is inscribed. If this is 5, well, it's a pentagon. That means we've done this before. 360 over 5 turns out to be 72. This whole thing is 72. And once again, we just draw our apothem here, which we know bisects the side and bisects the angle. If this is 72, then this half angle here must be 36 degrees. Now what we want is the apothem here. We know R, and in that case for this triangle, this is our hypotenuse. So what is adjacent over hypotenuse? That's AH. Let's see, some old hippie, that's opposite over hypotenuse. Cut another hip, A. A for adjacent, hippie for H. So, cut another hippie, that's cosine of 36 degrees equals adjacent, that's A in this case, that's our apothem, over the hypotenuse, which they gave us. That's the radius. So we just get that A equals 5 times the cosine of 36 degrees. They didn't ask us for the apothem, but that's something you need to find if you're going to have any hope of figuring out the area of this pentagon. Now that we have this, we'll come up with a number in just a minute. We're also going to need a side length. Remember, our formula is 1/2, and they didn't give us a perimeter, so we might as well just use side length. A, we figured that out. N, they gave us that, it's going to be 5. S, well, what would S be here? Well, again, we have a right triangle, and we just figured out A, and we know R. So this side here, this little piece, which is half of S, don't forget that, but we're going to find this, and I guess we'll just call it X, because that's what we're looking for here. And we're going to have 5 squared minus A squared. This is our hypotenuse squared minus one side squared. The square root of that is going to give us X. So if we plug this in here and calculate, we should be able to get, when we get X, we're going to have to double it, and that'll give us S for our formula here. So if we finish off this square root here, we found A, 0.045, cosine of 36 degrees is 0.809 times 5. We get this. If we square A, in order to get X here, we get R squared minus A squared, or 25 minus 16.36, and we take the square root of that. This is about 8 point something, and square root is 2.94. We multiply by 2 in order to get one side here, which is almost a waste of time, because after we multiply it by 2, we're going to divide it by 2 up here. But in order to keep all this straight and make sure that we have this solidly in our brain, we're going to go ahead and stick with S, the real S. So for the area, we should get 1/2 of A, that's 4.045. We plug in the actual numbers that we've derived for each of these variables. A is 4.045. Well, 5 we didn't have to derive, they told us it was a pentagon. And then 5.88 for the total length of a side, S here. Remember, X is 1/2 of S, or 2X equals S. We perform these calculations and get 59.44. Those are in square units, whatever units that we're using. So you see, graphing the circle was not too relevant. The part we really needed was this. You just needed to spot that for the equation of a circle, this part here is the square of the radius. The center of the circle, when it comes to computing the area, where you place the object is completely irrelevant. That's not true for polygons. I mean, not just polygons. That's true for everything. If you want to know the area of Africa, if you were to pick it up and move it to the Antarctic, it would still have the same area. If you don't believe me, try it. Well, you better check with the people living there first. They might want to move to Antarctica. Now, this problem is kind of like the concentric circles problem we had. And we just needed to find the area of every other annulus formed by these concentric circles. Here we have a bunch of figures. We've got a triangle inside a square, which is inside a pentagon, which is inside a hexagon. not as bad as it looks. It's not super easy, but it's not totally awful. The way you work this, just like with the concentric circles, we're going to find the area of the hexagon. And then we're going to subtract off the area of the pentagon inside. Then we're going to add in the area of the square. But of course, that'll give us too much, so we'll have to subtract off the area of the triangle. So let's see if I can write out what we're going to do right here. The area that we're looking for of the shaded region, it's going to be the area of the hexagon minus the area of the pentagon plus the area of the square, and then minus the area for the triangle. We got the hexagon minus the pentagon plus the square minus, so we're subtracting off the unshaded parts and just adding up the shaded parts. Negative, the unshaded parts are negative, the shaded parts are positive. You can look at it that way. And a lot of this we kind of already know how to do, don't we? We found the area of a hexagon before. With 6 sides, it's going to be 360 over 6. That's 60 degree for the large angle, or 30 degrees for the half angle, and it's 4 down here. So, right off the bat, we can write that opposite. We want to find the apothem, right? So we have opposite over adjacent. This is our altitude for the triangle, but that's okay. Remember, an apothem is actually the same as the altitude for the isosceles triangles that we've been working with to get the area of the entire polygon. So we can easily, right off the bat now, write that the tangent of half of 60 degrees, or 30 degrees, that's because we're just drawing this down here, and we want A, but this half here is 4. So once again, opposite over adjacent, and that's the tangent. So that's 4 over A, or, pardon me, A equals 4 over the tangent of 30 degrees. If we work this out, we get, I wrote it as A sub t. This is the altitude for the triangle. We're going to find some other apothems here, because we have other figures, and they don't all have the same apothem. Well, I used the right angle and tangent here to arrive at the altitude, but I said it wrong. This isn't 60 degrees because it's 360 over 60. Do things in my head and I say them wrong. They tell us it's an equilateral triangle, and we already know that in an equilateral triangle each angle inside is 60 degrees. That's why this half is 30 degrees. It's true that when we start looking for the apothem, we're going to end up with the same half angle here and 4 over here. So we're going to get the same apothem. That's kind of odd, but that's because of the angle here. It's going to be 60 degrees for the triangle, and when we get to the hexagon, it'll also be 60 degrees. But this 60 degree angle has nothing to do with the fact that we have a hexagon here. It has to do with the fact that the vertices in equilateral triangles are all 60 degrees. I think you could say I misspoke. Well, A for the square we don't need. We already know it's 8 squared. And maybe I should point out that each of these figures share this one side they're all regular. This equilateral triangle, each side is equal to 8. This square, well, here's one side here, and it's regular. Well, it's a square, so every other side is 8. Again, they say it's a regular pentagon. This side is 8, so every side on the pentagon is 8, and same for the hexagon. So these are all regular polygons with side equal to 8. That's kind of important too. So what about A for the pentagon? What's the apothem for that? Well, we know that if we were to draw from a center that was a bit farther out here, we connect up our vertices for the pentagon, we're going to get a 72-degree angle. We know that from previous problems. Or you could just write down 360 divided by 5 and you'll get 72. You cut that in half and you'll get 36 degrees. And once again we have opposite over adjacent. So what I should write, so for the pentagon, RA, we can find by writing that the tangent of 36 degrees, that's half of the large angle, is 4, that's half of this side, over the apothem. Or the apothem is 4 over the tangent of 36 degrees, and I get 5.506. Now we need the apothem for the hexagon. And since this side is the same, the only thing that's going to change is our angle here, which becomes 30 degrees. The hexagon has 360 over 6. That's 60 degrees for the large angle. Half of that is 30 degrees. And we'll have the tangent of 30 degrees is 4 over the apothem. But wait a minute. We just did something like that, didn't we? The angle for our equilateral triangle, that half angle is also 30 degrees, and that's how we found our altitude. So we can skip one set of calculations and just directly write that I should write that big, there we go. Come on. A sub h for the hexagon is the same as A sub t, 6.928. Well, good. Fewer calculations, the better. Now, what we have to do is figure out A sub h, A sub p, A sub s, and A sub t, and then do some arithmetic. I don't like the way I just said that. I should have said capital A sub h, capital A sub p, and on down the line. These A's are the areas. These little A's down here are the apothems. If that's confusing, sorry. But we've got the A sub t, little a sub t, that's the apothem for the triangle. Capital A sub t, that's the area for the triangle. So now what we need is some room to work, don't we? Might as well start with the smallest one. Capital A sub t, area of the triangle. We know our altitude, so we get 1/2 the altitude times the base. Well, that's going to be 1/2 of 6.928 times the base, which is 8, not 4. We need the whole side now. And the same as 4 times almost 7. Let's see what we get. So for the triangle, we end up with 27.712. For the square, well, I just went ahead and wrote it out. It's 8 squared, which is 64. Now for the pentagon, we once again write out our generalized polygon formula here. A sub p is the altitude, or the apothem for this particular pentagon. n is going to be 5. That's how many sides we have, and s, of course, is going to be 8. So we can write this out now that we've got a sub p, which is usually the difficult part in the whole thing. So we just lay this out. 1/2 times a sub p, 5.506, n, well, it's a pentagon, so n is 5, and our side length is 8. We want the whole side for this formula. Well, this is 40, and divided by 2 is 20. 20 times 5.506 is 110.2. And for the hexagon, we're going to do exactly the same thing. The only difference is A is going to be A sub h, which we already figured out right here. So for this one, we've got the general formula written right up here, except that we need A sub h. That's 6.9. So, I went ahead and wrote those in. 6.928, that's A sub h, times 6. In this case, n is 6. We got a hexagon. And the side is still 8. So 6 times 8 is 48. Divided by 2 is 24. We can write this out and then get this. So now if I give myself some room to work, we can go back to what we had up here on the top. This one here. We've got A sub h, A sub p, A sub s, and A sub t. I think we had A sub t here somewhere, don't we? Yeah, there it is, 27.712. If I hadn't written this line here, I might be able to just write it out right here. Let's try that. And with a little bit of luck, I might not run out of room. Let's see here. I can write equals A sub h. We found that down here somewhere. There we go. 166.27. Well, here's where I filled in the numbers that we found, and let's block this off here. These are all the intermediate equations where we found the a's. And then down here we started finding the areas. And now we'll go back up here once we have the areas and plug them back in, which we just did. Now all we have to do is punch this into our calculator or command line in Excel and see what we get. And at the end, if you do all this, you get 92.35. That's the area of the shaded region. Why is this such a good problem? And it is a good problem. It really is. Just like that concentric circle thing where we had to take the large one, subtract off the big one. Same thing here. We're adding something and then subtracting off something else. That's something you're going to do a lot of in set theory combined with probability. For instance, what you're going to do is have two sets like this, the A and B. Each one has an outcome probability. Probability for A and the probability for B. What's the probability of both of them happening? Well, you'd like to just put a plus sign in there, wouldn't you? Oh, well, it's this plus this stuff plus this stuff. The problem is all this. You're counting it twice. You're counting it in this one for A, and you're counting it over here for B. So now what you have to do is subtract off. I don't know if you're familiar with this notation, probably not, but this is a kind of a standard notation for A intersection B. In other words, the spot where they overlap, you subtract out. So you add the two and then subtract. And sometimes you have more sets. You can have other sets here, and you can have one big set here. And what you're going to be doing is adding and subtracting, and then adding bigger parts, and then subtracting off the small intersections. And you end up with something very similar to what we had up here, where you add them, subtract them, add them. Same thing we did with concentric circles. You're going to see a lot of this in probability. So these problems are really more instructive than you might think, because it's a good chance you wouldn't have to find the area of something like this very often. I could be wrong. But you could take a look at this. This kind of looks like a ring to me, like you wear on your finger. Well, if you want to know what the area of this was, you could just take the area of the hexagon and subtract off the area of the pentagon and forget all the other stuff inside. And now, this totally bizarre, irregular shape, you would have the area of that, as long as it's created by sticking another regular polygon inside of it. You can subtract the two areas and end up with what's left over, which may be a very odd looking shape. Well, that's about it for now.